Sweet. Let's go ahead and let me show you a couple of things. Let's navigate to our course. And so now, besides the Panopto that you have down here with whatever's working, I also have some videos that I managed to salvage left and right. One of them was the image stitching. You can click on that one. And the other one's the time series analysis that we did last time. And I'm basically going over all the old ones and trying to just salvage as much as I can. I'll do another one for today, all right? Honestly, I believe the time series analysis is the thing that you're probably going to be using in the future the most. And so you'll have at least one resource for it. And I was thinking about it, and I'm like, all of this is going to be gone the moment that you stop this class. So what I'm going to do eventually is I'm going to put everything up on a web space, probably my web page, dedicated to Digital Ag. It's going to be just one site that you guys can go and find these things later on. But if you found something that's very interesting, perhaps you need to make backups of it, copy it right now, okay, because I might forget. Having said that, I know that Moodle stays up for at least a semester or so, so you have until spring to be able to grab whatever you want. No? I think it's yes. You have to go and look at the old classes. But in any case, if there's something of interest here, you should grab that, and I promise you by the end of the semester, I'll make a copy of all this on my webpage so that you can find them later on if you'd like. The videos are all on YouTube, and so you can use them, so you can find them through there as well. Unfortunately, Panopto is going to be gone, but I was told that I can make it available, put a general license over there so everybody can see them. And you know what? I kind of don't want to do that because, I just kind of don't want to do that. First off, I hate my voice. I think that's one of the most disgusting things ever. So I don't want a lot of people to know that that voice exists out there. I do hate my voice. That is true. I don't like my voice at all. But yeah. As a preference, I don't like my voice. No, the reason is, I don't know, maybe there are a lot of typos. I'm not really comfortable in opening this up to the general domain. So I don't think you'll have the Panoptos. So if there's something over there that you think is interesting, just download it yourself. All right. Now what I'm going to do is I'm going to talk to you a little bit about time series analysis. And I have a presentation that matches the write-up that I gave you. Let's all go ahead and click on that one. And please download this whole folder and save it on your desktop. It's the same folder that we were working on last time, but we now have a different analysis that we're going to be working on. And I will start with a short presentation of what we're doing. Alright, apparently the PowerPoint was not saved. Blah. Because I worked on it on the other computer. Well, that sucks. Okay. So, you downloaded the PowerPoint? Oh yeah, so it's here, but it's not over there, right? So it hasn't downloaded yet on mine. Alright, so I'm going to talk a little bit about this. Okay. One of the most important analysis that you can do with the time series, besides finding like maxes and mins and average and smoothing and all that stuff, is the idea of forecasting. Now, forecasting basically means I'm going to use some information from the history of that time series to predict how that time series is going to continue in the future. Okay? You can understand why that might be very, very useful if, let's say, the thing that you're forecasting is, I don't know, the price of stocks. If you could somehow read from the history of stocks how it's going to behave tomorrow, then you either buy or sell today and make millions. Okay, of course, that's a little bit hard to do. And the first question that I want to address is when to forecast. Some things are much simpler to forecast than others. For example, I can tell you with mathematical certainty that the sun is going to rise tomorrow, and I can also give you an approximate time for that. And I can be as thorough as I can about it. Right? We can more or less figure out when the sun is going to come out tomorrow. But we don't really know what the price of Google stock is going to be tomorrow. Right? For both, for the sun and for Google, we have all the historical data going back to, in the case of the sun, hundreds of thousands of years. In the case of Google, a couple of decades. But still, knowing something about Google doesn't tell you how it's going to behave tomorrow, because there's so many different things going on in the background. Whereas the sun, it's simple physics. There's a formula that does that. So what's the difference? For the sun, there exists a formula, and even if you don't know it, you can approximate it using forecasting. So there is a mechanism that can be described by looking at the past. All right? When you have situations like that, forecast is simple. When you don't have situations like that, aka Google stock predicting, you can't. And we have, as I said, various factors that help you predict something. Number one, how well do you understand all the things that come into it? Right? As I said, for the sun, it's simple physics. You understand all the objects around there. Done. For Google, it's all sorts of things, right? How the markets behave, what the heck happened last day, what's going on with Google itself, all sorts of craziness. How much data is available, all right? It's much harder to do predictions when you only know like 2 or 3 values of the time series. But if you have a couple of years worth of it, perhaps you can identify the trends and you can see it in the future. So theoretically, the more data you have, the better it is. But that could backfire as well, because your data may have changed drastically from the past 10 years. And what trends you had back then no longer are there. So too much data somehow also might conflict predictions. So there's a sweet spot over there where you're using good data. Data that is current and data that is capturing the trend. And a very important thing here that people tend to forget is whether or not the forecast you're generating actually affects what you're trying to forecast. So that has happened more than once with economies. When you have this great model that predicts something in economy, and then people know about that model and read that index and believe in that forecast, then basically change the whole parameters of the problem, and you get something completely different. So there are situations when knowledge of that forecast actually changes the future. And let me give you a simple example. What if I knew with a high enough certainty that Google's stock is going to fall tomorrow? I start selling a lot today, right? So then instead of falling tomorrow, now the price is super cheap and people come in and buy cheap Google prices tomorrow, and eventually it rises instead of falling. So, that's an extreme case and it doesn't happen in practice, but it has happened in the past. For example, you can have forecasts of the price of oil. That has actually been a self-fulfilling thing in the past, when the United States, after the war of the Gulf, were believing that the price of oil is going to go up. They started stockpiling, and then at some point, they had so much oil that they started selling it back in very low prices. So then the Arabs had to counter that and lower their prices themselves. Instead of oil going up, oil went down. So, yeah. It was affected by pre-knowledge that we had about the forecasting. So it's a little bit tough to forecast in general. And the other question is, what if things change? Okay, so you forecast by saying, the future is going to kind of look like the past. But what if things change? And what I'm going to try to show you today is that we are actually thinking that things are going to change. A good forecasting model captures even that. It captures, how things changed in the past, and it can predict how things are going to change in the future. So we're not assuming that the model is going to stay exactly the same. But what we need to have is that the way things are changing is not going to change. All right? So things could be changing daily, yearly, monthly, whatever, but they won't vary that much from this year to the last year. So for example, you could have prices increasing daily, right? And you can keep on predicting that increase in the future. But what if prices in the past rose slightly and then at some point they start going around wildly? So a good prediction model keeps intact the change as long as the change doesn't change. Does that make sense? Okay. All right. So not only where it's going to be, but also how it will change. What is forecasting in one sentence? It's predicting the future as accurately as possible, given all the information available, including historical data and knowledge of any future events that might impact those forecasts. Okay, that's forecasting in a nutshell. If you guys want to put that in any poster or anything like that, quote me on this. But besides the forecasting, you need to keep in mind, you need to have some goals. You can't just do forecasting for the forecasting. You need to come up with a plan. Why are you using this? Who's the person that's benefiting from it? Okay? And instead of just going out there, doing a couple of forecasting and then coming up with what you want to do, it's much better to say, okay, I have this goal. What would be the right forecasting? What is the right data that I need to collect? Okay, so do it in a principled way. First come up with goals, then do the forecasting, and at the end, do the planning. So what is planning? I have my goals, I've decided what the right forecasting is, and I'm moving forward with those. This is much better than what most people do out there, especially people that are not data analysts, that have somehow collected their data set, and I'm winking at a couple of you guys, and then they say, okay, let's make sense of this data set. Let's try to predict using this data set. That's not the right way to do things. The right way to do things is say, I have this goal. Let me build up a forecasting machine of that goal. Let me collect the corresponding data. All right. When can you forecast in this class? Only if we're talking about numerical data. Okay, there are other forecasts out there that do things like Boolean or even characteristic. We're only going to be doing numbers. Okay, so time series numbers, and we're going to figure out more numbers in the future. And also, we will assume that some of the patterns in the past also continue in the future. Okay, there are elaborate models out there for non-numerical values, and also there are elaborate patterns, algorithms out there that do crazy analysis in the future. We're just going to do the simplest stuff. But for things like weather data and for things like yield data, if they are periodic over a year, more or less, these types of approaches work. Okay. And final thing here, it is not just for you that you're making the forecasting. So it's not just I'm going to do this little thing, present this at a conference and forget about it. It makes sense to take the forecasting and change it back into some sort of action. Something that people can use and work with and figure out when they plant their fields and figure out which type of fertilizer to put when. Right? If you just do forecasting for the sake of forecasting, not very useful for us. Okay? All right. I'm going to pause this one and I'm going to come back to it. I have to talk about a few more things, but I want to see them in action. So download this folder and we will be working with the analysis 2.1. It's the the link that you found on Moodle for today's daily task. All of it, yeah. Download it, save it. And on it, we will be working with the analysis 2_1. All right, first things first. As usual, right? Let's go ahead and put all these libraries. And I'm not going to be using all these libraries, but these are the key libraries for doing time series analysis. So let's make sure we have all of them. Clear and Reshape are basically data analysis tools. They allow you to change things around, but they can also be applied to time series. ggplot is our favorite to create graphs. Read Excel. Well, most of the times the time series that we get are in Excel, therefore I like it there. And Foreign, just in case we have other ways of putting in the data, like database files or JSON files and whatnot. So Read Excel and Foreign would allow us to read practically all types of time series that are out there. Now, especially for time series are the packages Forecast, T-Series, Lubridate, that takes care of dates, XTS, which is another parallel way to do time series, apart from the TS, and the TS box, which is a package that allows you to travel from data frames to time series to XTSs to all that stuff. Now there's another one called FPP2, and I will put it in here, but this is a little bit experimental, so it might not work. Right, so FPP2. Add that as well. Okay, this works. Right? So if you don't have these packages, please start installing them one by one. We know that there's this install button down there. Try your best and install all of them. Let's see. Okay. All right. Now let's see if this one works. Don't forget also to set your working directory to source file location. Okay. Now I'm going to my favorite use packages, which is actually quite helpful now, because we have packages that are working with. And I want the first package to be Forecast. That is the one that trampled everything. That's why I put it first. Forecast, the list goes first. Now, let us read. Is everybody okay with the packages? It install for everybody. If the FPP2 does not install, remove that one. FPP2, that was an extra that I put at the end. I actually found out about it. I'm basically going to use the Forecast, T-Series, Lubridate, and TS box. And of course, ggplot. What's this FPP2 is again a package that does the same thing as the Forecast, which is the new package that finally came out. That has the stable forecasting. Now he has created the I'm not sure. I just saw it in his book, and then I saw his new version of the book, and it said that everything is now migrating to the FPP2. So FPP2 contains forecasting. I don't know what it is. Right? So if it doesn't work, Everybody okay with the libraries? Right. Let's go ahead and read the data frame weather from XLSX. So let's run first 3 lines to load our packages and also read our data. If you've done it right, it should read the data set. And as you can see, I have the data set inside the subfolder row data. Oh, by the way, I don't know if I've mentioned this, but this is how I like to write my code. My code is in the general directory. There is one subfolder which I keep my data. There is one subfolder that I put the results. Okay? So what I see here are basically some supporting files and just the codes with different 2.1, 2.2, and so on and so forth. And I kind of like this because it keeps things tight. So if I want to read the data from the raw data file, right? You see how I do it? Inside here, the read Excel /raw data takes you to the subfolder raw data. Right, so you're in the parent directory, /raw data, you go to the subfolder raw data, then you find this. Alright, let's go ahead and click on this or type view and figure out what this one is. These are the maximum and minimum temperature, including cloud covered, as we said last time, in the area in the Lafayette area where the Rice Research Station is, and they date back to 1999, and they go all the way up to 2014 in daily increments. Okay. The important variables for us is the maximum temperature and minimum temperature. And Tommaso, do you remember what the formula is that gives you the growing degree days? There is one, right?
Is maximum temperature minus plus minimum temperature divided by 2, the average minus the base temperature.
Okay. And that has something to do with how much energy, let's say, the plants get every day. Okay? That's, you know, a very crude measure, but yeah, useful. If you can figure out how much energy the plants get from the sun, that's a good indicator. All right. So what I want to do now is I want to try to identify patterns in the maximum temperature. Yearly patterns, seasonal patterns, and so on and so forth. And then extrapolate that to the year that I'm missing. If you scroll down here, you will see that the last date that you have is December 31st, 2014. So my goal is, let's try to figure out the first couple of days of 2015, and then let's try to figure out 2015 in general. The maximum temperature for 2015, the first few days, or maybe the whole year. Okay? If we had data that reached up to today, you understand how we can extrapolate, and we could figure out, for example, what's going to be the maximum temperature next year. And why is that useful? Well, it is useful because if you know things like that, then you can figure out when is the best time to plant, when is the best time to not plant, when is it, right? And if you had a couple of more knowledge, if you had a similar series here for the rainfall, you could extrapolate when is the best time to get as much rain as you want. Alright? These type of questions. Alright, let's go back to the code. And as I'm going through the code, what I would like you to do again is put comments line by line as we normally do, right? So this first line basically reads our data frame. And what I want to do is I want to shorten it a little bit. And I'm going to keep only the dates after 2010. I just do this for things to run faster. There's no other reason. Right? It's much better to keep all the time series, but when I was doing the last few things, if I were to keep the whole time series, it was very, very slow. So the next line creates a subset of the original data set by cutting off the date to be everything greater or equal to January 1st, 2010. Now, couple of things here. If you look at the data set, one of the columns says date. There's a high chance that R reads that as a date. But if it doesn't, you can always transform a column. You need to basically say, you can put that as an extra line over there. You can say df dollar date equals as dot date df dollar date. So if the column date is not read as an actual date, you can make it so. And you can put this, an extra line here that says df date equals as dot date df date. Let's see if I can make it a little bit bigger. Does this look better? Okay. Should work with a plus plus, but it's and alright. So what I'm doing with line number 6 is I'm basically forcing R to view the column date as date. If I run this, and I look at my data set again, don't really see any changes, but now I am sure that R sees the first column as dates. Because you can understand it's a little bit tricky to say things like greater or equal to a characters. But you really wanted to, let's say, find everything after 2010. If you don't want to convert it to date, you can put it in this subset argument where I'm saying view the column as dates and make sure that these dates are greater than 2010, greater or equal to 2010. Okay, so line number 7 basically chops off the beginning and just keeps the last 4 years. And we notice that df is like a big data frame, so I only really want to keep the date and the maximum temperature. I don't need anything else. So this line basically tells R to keep the first 2 columns. So it says all the rows, so empty comma, but only columns 1 and 2. Basically I wrote it as the columns from 1 to 2. So columns 1 and 2. Now you're left with this nice data frame 2, that only has the dates and the maximum temperature, nothing else. Are you with me so far? Any questions? Fantastic. Now, this is in a data frame form. In order for us to do analysis, we need to change it into a time series form. So the next line takes as input a data frame, and converts it into the object time series, which is the thing that we use to analyze using forecast and all that stuff. Right? Which is basically a little conversion. I'm going to name my time series max temp. That's the name that I choose to give the time series. The command to convert it into a time series is just TS. So TS what? TS the column max T from data frame 2. And then you just need to tell it where to start it and whether or not you're doing days, weeks, months, or years. So, start at, and it's a little vector that tells you year, month, date. And then frequency. Frequency is 1 for year, 12 for month, 52.25 for weeks, and 365.25 for days. So I know that this is daily, I need to put 365. Great. Grab that line and run it. And now, nothing was destroyed, but you now have another little argument down here. It's not exactly a vector, it's a time series. It's a vector that you know something about the input. If you want to see that vector, just highlight the max temp and run that one. Okay, and you just get these values one after the other. These are the max temperatures. Fantastic. Now, the package forecast has a very fast way to visualize time series, and that is the autoplot. So if we grab this line and say autoplot the time series max temp and run it, we get a very nice little plot here, which is basically this time series. As you can see, it starts from 2010 and goes over to 2000. Okay? And autoplot takes any time series.
So for this time series, is it allow you to have like more than one variable to the maximum temperature?
Yeah.
Then you can the same time?
Right now I'm dealing with just one. Yes. In order for us to treat that, we need the package zoo or the XTS. And yes, you can have vector time series. But for us, let's focus on just one. All right, so that is how you do the autoplot in forecast. That's good and fast visualization. And autoplot basically uses the same thing as ggplot in order to create the graphic. So, you know what? I kind of want to see better graphs on that one. So the next part is how to graph it, but without seeing it as a time series, instead seeing it as a data frame. So again, I'm creating a ggplot where I'm graphing a geometric line using data frame 2, and the x-axis is the date, the y-axis is the maximum time. And the reason why I want to do that is because now I can put, you know, different labels. I can change everything that I can change ggplot, right? I can different colors in the background. So this will generate basically the same image, but using ggplot, so I can, you know, beautify it if I want to. Also, it gives you the ability to save it. So that's what the next line does. Let's go ahead and rerun that one. It creates a ggplot and saves it. Again, it also output. And as you can see, it looks exactly the same. But now I have changed here. This is maximum temperature, date. You can do whatever you want, right? You can literally ggplot everything. Put different titles, change the background, change, you know, the ticks, whatever. All right, and I'll keep doing that as much as I can. You can do similar stuff with autoplot, but not as many. All right, now last time we talked a little bit about a moving average. That was that smoothing process, which you replace the function, the time series with the average of the time series a couple of days past and a couple of days in the future. So to do that, let's go ahead and create two more columns. The first one is going to be taking the maximum temperature and is going to be doing a moving average of 7 days. And the other one is going to be doing the same thing, but with a moving average of 30 days. So what I'm doing with these two lines, I'm basically extending my data frame 2 by adding the moving average using 7 days and the moving average using 30 days. So two more columns. Let's run these.
Moving average is centered.
Yeah, these are centered. Yep. If the default is centered. If you want to change it, you put comma, centre equals false. And you have options there. You can put it to start from the previous 7 days and going up to that. To figure this one out, what I would do is I would look up MA. Do a little help search on MA, and you can see it tells you moving average. MA stands for moving average. So now if you see our data frame 2 just got 2 more variables, right? This is the moving average with 7 days, this is the moving average with 30 days. And obviously you don't get any value for the first 3 days because you don't have enough days prior to that to compute it for the moving average of 7. And you don't get any value for the first 15 days if you're doing a moving average of 30. Because you don't have enough values before that to do the computation. And you also don't get, right? Because how would this be computed? You would have to look at the 3 previous days here, the 3 days after this. There are no 3 previous days. So you cannot do this computation. It's only when you reach here and you have 3 days before and 3 days after.
How does it calculate for each row?
Right. So you go here, and what you do is you take these 4 and then this other 3. So it's 3 above, 3 below, and that one, and average. 3 before, 3 after, and that one. And for the 30, since it's even, it actually takes 15 before and 15 after. Okay? So the first value you get is for 16. And you can understand as I'm moving down to that, there's going to be also a problem as I'm reaching the end. Right? I'm going to be missing the last 3 for this and the last 15 for that. It's a technical thing. You're missing values in that computation of the moving average. Right? Now, that's okay. I mean, I'm missing a couple of days. That's fine. All right. So what I want to do now is I want to plot the original function, the moving average with 7 days, and the moving average with 30 days all together. And again, I'm going to use a ggplot because it makes a beautiful graph. It's actually quite simple because on the x-axis you always have day, and on the y-axis you just have the different variables that you just create. And by doing plus plus plus, you have everything on the same graph. Right, so ggplot again, and the geometrical line, that's how you do time series using geom_line. And all 3 of them, the reason why I like doing that is because I want to have a colorful map that looks kind of nice. Right. So let's grab this next few things, and also notice that ggsave saves your result in the graphs one. So let's go ahead and run this, and it might not look very well, very good, but if I zoom into it, as you can see, this looks very nice. Okay. So the green one is the raw data, and if you really zoom in here, you will see that the weekly moving average is also jaggedy, that blue line, but then when you look at the red line, it's much more smooth. But you know, all of them kind of follow the same pattern. That's the idea that I want you to keep. You can go back, if you don't want to see all that, you can go back and just, let's say, if I comment out, I don't know, the raw data, and rerun that one, this just gives me the moving average for the month and then for the year. So if you like to see the 2 smooth average, you can do it like that. All right. In practice, most of the time we plot the raw data in one smoothing average that we decided to go with. Both the 7 makes sense and the 30 makes sense. By 7, we're saying we're doing weekly averages. By 30, we're doing monthly averages. Both make sense. Other folks do also quarterly. That's too much for these types of things. Are we okay with this? Let me go back uncommented because I actually like to see all 3 of them together, and rerun it and save it. You can get the same result by converting the previous time series that we have, the max temp, into a smooth time series. So we can apply moving average in the time series. In this case, you need to tell it what order. So this line does it on the data frame. This line does it on the time series. So what I'm doing here is I'm creating a new time series, which I'm calling monthly max temperature equals moving average of the max temperature time series that I had before with order 30. I'm not doing a weekly one. I'm actually going to be continuing on with a monthly one from now on. And if you auto plot that guy, this will just give you the time series corresponding to the monthly smooth version of the max temperature. Okay. So you can work on it using the data frames, or you can work on it using the time series if you're trying to present. And honestly, I prefer to do it with the data frames because then I can graph it, it looks nice, and you can multiple graphs. But from now on, we're going to focus on the time series. So you can't really do time series analysis with data frames, right? Okay. So after we do a graphic representation, we notice the following. Do you see a pattern? Yes, you do. You see a pattern right there. Is that pattern logical? Of course it is. Maximum temperature drops as you're getting close to the change of the year. Winter time. We notice it now as well. Maximum temperature has dropped drastically. And then it goes up again for the rest of the year, obviously, right? There's a little drop over here. I'm not sure what that is, but it happens around the summer. It could be hurricane season or whatever. I mean, something's going on over there. But then if we disregard that little bump over there, it's literally some sort of sinusoidal function that goes up during the summer and then goes down. You all know how that works, right? Earth turning around the sun. We know this like this. That's true too. Something's going on, more pollution in the house. But in any case, the question now is, can we glean a couple of information? Try to figure out three things: trend, seasonality, and simplicity. Let me pause what we're doing right now and talk about these three things. So back to the presentation real quick. So, what is a trend in a time series? A trend exists if you look at the time series long term, a couple of years. Does it seem to kind of drift up, drift down, or what does it do? Does it bounce between things? So it's, if you stop looking at it as the actual change, but looking at it as what does it do overall? Is it a bouncing thing that is increasing? Is it a bouncing thing that is decreasing? Or what I tell my students is that squint so that you see it as a straight line. Is that line going up or is that line going down? If there is a upwards trend, you would see these bumps going all the way higher and higher and higher. If there's a downward trend, you have the opposite. If there is no trend, then we'll be just repeating. So that is the trend. One key component in a time series. The other one is seasonality. Seasonality is this repetition, this period that's going on. What we have identified, up during summer, down during winter. The seasonality is this repetitive, periodic pattern. That could be repeating at the same frequency, as we say, in regular intervals that keep on being the same, or it could be drifting a little bit. Okay, the frequency may be changing. Finally, we have cyclicity, which is not exactly like trend. The trend will just take you up. Cyclicity is something like you see a trend that's going up, followed by a trend that's going down, followed by a trend that's going up, followed by a trend that's going down. It's a long-term pattern in your data. So you have the short-term patterns, which you call seasons, and you have the long-term patterns, which you call cycles. One cycle is actually the cycle that the Earth is on. We have some ice ages followed by non-ice ages. So that's a cycle. It's in like millions of years. During each cycle, we have seasons. Climate and weather. Weather is seasons, climate is cycles. Agreed? Or did I say the other? No, that's right. Got it? So that's the difference between the two. So now what's happening is you have your trend, you have your period, and you have your cycle. The sum of all these three things is your data. So all of these three things contribute in giving you the daily data time series. So what we're going to be doing in just a second is we're going to be decomposing our time series into these three things if they exist. All right? So in order for us to do good forecasting, we need to identify, if possible, the patterns and then choose a method to capture those correctly. So what we need to figure out is the trends, the cycles, and the seasonality. Agreed? Let's go back and see how we can do this in R. There is a function in the forecasting package that tries to do that automatically for us. And that is called decompose. So decompose basically says, just like I told you, there are these three things plus a little bit of error, and they're all added together. Try to find the best breaking. So decompose into the components. And how do you do it? You do it additively. So let's go ahead and try to decompose the MT max temp. So from now on, I'm going to be using the smooth version with 30 days, right? I'm not going to be using the original data. I'm just going to use the smooth one, the monthly smooth. So this line basically decomposes this into, you'll see in just a second. So let's run this one. This one does the decomposition. And then if I auto plot the decomposition, you'll see what I'm talking about. So the decomposition is, so this is your original data, right? And it says, this is basically the seasonality. The trend is, it was going up a little bit from 2010 to 2012, and then it started falling down until 2015. And then there's some extra jittery stuff over there, which we call trend and error. And there's always going to be something. It's not, I mean, this is not a math model where it completely breaks. Now, how this one is done, you don't worry about it right now. There is a theoretical, this is based on the Bayesian approach on how to decompose these two things in such a way that it makes the most sense. Just like that. But for us, here's how your pattern looks like. If you're looking at the seasons, it's always like goes up to plus 10 degrees, minus 10 degrees. Then you have a trend. So the average is around 78, but sometimes it goes up. It went all the way up to 81, and now the average temperature is down to 67. You find the average temperature of the year, and to that, you divide a plus and minus 10, and this will go. And to that, you add a little bit of randomness.
So average for the year, like
We want, it's actually not for the year, it's for the average for that year.
okay.
You find the average for that period, not the trend is how it would look like if there was no seasonality. If you get the average per season. Seasons here, a year. So how would you move over the year? To that though, because you have seasonality, you need to add or subtract up to 10 degrees using that rule of thumb. And to that, you need to add a little bit of noise. And the noise can go up to plus or minus 4 or plus or minus 8. Okay? So that's what we did. We decomposed our series into trend, season, and noise. Okay? So, you will hear, find me the D-trend time series. D-trend is nothing more than you take the raw data and you remove the trend. So what you're basically keeping is seasons plus or minus noise. To do that, it's very straightforward. When you're doing the decomposition, I saved it as decomp. If we look at what decomp has 6 things. It has the original, it has the seasonality, the trend, the random. It tells you what type of seasonality it is, and also has the figure that captures everything to create it. So if you do decomp trend, that will give you just the trend. So if you want to detrend something, subtract that from the original one. So what this line does is it takes the original one and subtracts the trend. And what you're left with is basically the seasonality and the noise. And I name that D-trend. Agreed? So I create a new time series, which I call D-trend. How do I do that? I use the time series that I started off with, and I'm subtracting the trend. And if you plot that one, this is the D-trended series. You can now see the seasonality popping up a lot more, but it's not exactly perfect because it's also adding in the noise. So in a lot of predictive models, I will say detrended first. That's how you do the detrending. The other thing that people ask is de-season something. Just keep the trend and the noise. So I create this new time series, which I call D-season, which is the maximum temperature minus the seasonal part of the decomposition. And when you auto-plot that, you basically get the trend plus the noise. So this would be the maximum temperature if we didn't have seasons. But we do have seasons. Are you with me so far? Okay, so we talked about 2 aspects. What is being used most of the times is the denoising. Okay, so the denoising part is, if you go back to this graph, this is your real time series, and these are the stuff that you can't predict. So you take the real series and subtract this stuff. Perhaps whatever is left is very easy for you to predict. Most of the times we do analysis on the denoised part. Definitely in the I do this, I do this, I do this. I always do smoothing, denoising, trend analysis. That's how I do it in my predictive models. And it works very well. So basically, in the case of the weather and climate, if I'm trying to approximate climate, I better suppress weather. If I'm trying to predict daily prices, I should predict random errors. I should remove random errors. That's the denoising part. So what I'm doing right here is I'm creating a new time series, which is the original one, minus the randomness, minus the noise. If you want to see this one, this is the time series that has the, whoops, I'm not sure this is the right one. No noise maximum temperature is MT max temp minus decomp. No, this is correct. So this one is the actual time series that I'm trying to predict without any noise. And I'm going to try to use that one to do my predictions. Here's the problem though. When I do this subtraction, I have some empty stuff in the beginning and some empty stuff in the end from the smoothing out and all that. So you must spend one line to throw these out. If you want to find, for example, the standard deviation of this thing, if you do it without the NA omit, you're going to get into trouble. So here, I want to find the standard deviation of the noise. And to do that, you have to put the command NA omit. So this one is going to look into your time series, and if there are any NAs over there, it's going to remove them. And then you have to look at it as vector, because the standard deviation can only be applied to vectors, not time series. But if you have a time series, you can change it into vector by just using as.vector. So it takes the random time series, it drops the empties, changes it into a vector, computes the standard deviation. So I want to find more or less what's the standard deviation of the noise, and it is 2.49. So 2.49 degrees is the standard deviation of noise. Things that you can't explain with patterns. And what I want to do next is I want to keep the one that doesn't have the noise and also drop all the NAs. So to do that, you create a new called clean max temp, and if you put the command NA omit, it just drops all those points that it doesn't have values for. So clean max temp, if you want to auto plot that, this function right there. Okay. So what did we do? We smoothed it out using 30-day average. We broke it into pattern, trans-seasonality, and noise, and we subtracted it. Okay? Everybody okay with this? Good. If we try now to decompose this series, let's see what happens. You see what happened now when I try to decompose it? The original data is practically just the seasonality, the downward trend, and although the noise might seem large, look at the scale. The scale like 0.4, so it's like practically nothing. So this new decomposed one, by design, if you like, doesn't have noise. It's only seasonality and trend. Now, you will be very lucky to have such a thing work. Most of the time you don't do it well, even if you do motion. But let's say for patterns like the weather, this weather could be like rainfall, or maximum temperature, and it's much easier now to predict this guy, that noise, than the other. We use this idea to predict. Does that make sense? Any question over there?
What is it you don't have a line that shine the noise prior to the
Prior to that, I had to remove a couple of NAs. Right? The moment I did that, I lose a lot of information in the areas where I was missing a little bit of information. So that's my real problem.
So just removing the ones that are missing data points?
Yeah. We did that when we created the clean max temp. So then it's hard for it to calculate trends in areas where you're missing data. But that's okay, right? We have all the information we need for 2011, 12, 13, and 14. Agreed? Very good. Now, in order for you guys to do prediction, your time series needs to have one property. I'm going to say it out loud, and I'm going to also give you the formula for it, but I'm not going to delve into it too deep. This property is called stationarity. stationarity or time series stationary if the average of this, the variance of this, the correlation of this with itself doesn't change if you move to the future. If you have a time series, right, and you're viewing it basically as just numbers, if you fix those numbers for the first 3 years, compute the mean. Go then 3 years in the future, compute the mean again. Take all these things together, compute the mean again. Do that for the next 10 years, take the mean again. If that is always the same, independent of how many years you view in the future or how many years you view in the past, if the variance does the same thing, then you call your process stationary. And you can understand if you have such a process, it's much easier for you to predict it. Right? Because there's going to be a lot of patterns going on in the background. So a stationary process is the one where the basic characteristics that we check in statistics don't change with respect to time. It might change a little bit, but they don't change it for long periods. And there is a test, just like the test that we learned in 705 that checks stationarity. It's a p-value thing. The null hypothesis is the time series is not stationary. So when I run this test, the ADF, automated Dickey-Fuller test, this gives me a p-value of 0.0148. So you have to reject the null hypothesis. This is stationary. Every time you have a stationary time series, it's not easy to do. If it's not stationary, you have to somehow convert it to there is a very simple way to convert the stationary to time series and subtract itself. But I'm not going to care about that. Let's talk also briefly about what the autocorrelation function is. How many of you guys know what the idea of the correlation is? Okay, you have this set of values and this set of values. And you're trying to see if these two are correlated. Remember that from the 705? That is the correlation function. Well, the autocorrelation function is you have these set of values, and then you take these set of values and you shift them one down, and then you compare these with these. So you're comparing these values with themselves moved one to the future, or one to the past, or two to the future, two to the past. So there are many autocorrelation functions. If something is autocorrelated with itself, it means that there's a lot of repetition. That's basically what's going on here. So if I run the autocorrelation function with this, we will notice that our time series is correlated with itself highly if you do 365 lags. So this is, you can understand it, right? This time series, if you move it by 1 year, and you look within match, even if you move it by half a year, they match inversely. That's what it says. We have something which is close to -1, they're negatively correlated. So your time series is negatively correlated with itself if you move it half a year in the future. And it's very much correlated with itself if you move it up a year. So again, take your time series, shift the year. Does it match? So the props match, yes, they're highly correlated. Shifted by 180 days. They match inversely. This is a rally, this is negative. So that is the idea. So this one, if I read it, it tells me that my time series repeats roughly every 465 days. Okay, so that's how we read the autocorrelation function. I also have the partial correlation function. I'm just going to run it. It's a similar thing. I don't want to get into that. We need a little bit of calculus 3 for this. But it's something that we put out there. And we go now to prediction, the very first thing that we're going to try to do. So, what is this autoregressive moving average, the ARIMA? What this one is doing is it says, okay, I'm going to take the function and I'm going to view it as some sort of formula of what happens in the past. Okay, so I'm going to say, let's say, f of January 1st is a function of all the previous ones, okay? And so then I'm going to see what type of function is it. Is it a linear function? Is it an exponential function? ARIMA does by default linear. And it says, basically, can I predict the value of day 1 by looking at X number of days in the past? The X number of days is given by this, the C30. So what I'm telling it now is predict the value, the day of the future, by looking at 30 days in the past. And try to, again, train a linear model that will give you, let's say, January 1st if you're looking at the previous December. And how do you train that linear model? Well, use the formula that you have used. Now, let's not worry about this one. This is for the drift, and this is for the trend. Let's not worry about this one. This is the important stuff that I want you to do. So basically what I'm trying to do is I'm trying to predict one day by looking at the previous 30. You can increase this as much as you like. Unfortunately, R stops at 100 because the computations become very hard after this. It crashes actually after 100. So you can do it by at most 100 days past. So this one creates a model that predicts one day by looking at the previous 30 and saves it as fit. As you can see, it will take up a little bit of time. Run it now and we'll see what happens. Obviously, the larger that number 30 is, the more time it takes to computation. Imagine what's going on in the background. I have an equation that has 30 inputs and 1 output, and has 30 weights. Correspond to the best 30 weights. The best 30 weights is change the weight until you pick the pass. It's going to take a little while for that to compute, but the moment you run it, the next line is going to do use that model that you have and forecast on it. So that forecast is actually a function. It says use the bit that you have developed and forecast for 30 days. The h equals 30 is the number of days I want to forecast. And I'm forecasting using the model fit that I have created just a moment ago. And of course, I want to auto plot all that. What you got over here, and let me make this a little bit bigger for everybody to see, is so as you see over here, I've created my model, and then I went all the way to the end over there, and I predicted 30 more days. Just 30 days. Here's the thing. You can predict as many days in the future as you like, but the accuracy goes on. The shorter the period you predict, and the bigger history, the better the prediction is. The blue lines that you get over there is 8%, 9%, 95% confidence interval, just like the confidence intervals that we learned in statistics. As you can see, the trend kind of repeats. This is the best prediction that you can get for 30 days. If you change this to 10, this is going to give you the prediction of the next 10 days. And this is actually a much tighter prediction. So the confidence intervals are closer to this line. Now as you're moving forward, these confidence intervals become larger and larger. For example, let's try one here that does the whole year. And as you can see, this is clearly not good. Right? If you go a year out, there is a point where there's no real prediction. So, this autoregressive moving average is a fantastic tool to predict tomorrow, predict 5 days from now. Then, okay? And how does it do it? Again, it has trained it in such a way. Use the previous 30 days to predict the next. Are you with me so far? And the Solar Arduino does that for us. No problem there. Alright. I want to make sure that I leave 10 minutes at the end, but let's go ahead now and answer the following question. Okay, but what if I really, really want to be able to predict the whole year? What's the best way to do it? The method that I'm going to show you works only if you have highly seasonal data. It doesn't work in general. So do not use this formula to predict the stock market tomorrow. That's not going to work very well. But you can use this algorithm to predict the max temperature, minimum temperature for the next year. Here's how you do it. First, you decompose the cleaned version. Right? This is the cleaned version. And from that, I'm only going to keep one season. Let's say either from 2011 to 2013, 2011 to 2013 to 2014, just one of those. Okay, not all seasonality. So the next line, the year season window, the command window basically chooses a period from this time series. So my window starts in 2013 and ends in 2014. All right, let's run that line and see what happens. And so what I kept was just the seasonal trend for 1 year. Agree? And it doesn't really matter which one. Most of them are practices. Since I'm going to be doing some additions and whatnot, I want to convert that back into like some sort of vector, data frame, or whatever you want. So to go, another way to go back into vectors from time series is to use the command unclass. This one here, the year season, is a time series. If I want to see it as just a vector, I need to unclassify it. So unclass year season, and naming it into year season vector, basically just creates a vector that contains all these values. Okay. So here's what I'm going to do. I'm going to take the seasonality. Then I'm going to go to the last value for 2014. What was the last maximum temperature of 2014? And to that, I'm just going to add seasonality. I'm going to take that in 2015. Exactly about 2015. Let's start with. So the next line, basically, I had to figure out what was the last. So it says last in 2014 is the subset DF2, where the date is, I should have put over there, equal, not greater than equal. So basically, this line 62 tells me what was the very last maximum temperature that I had in my test. Goes to the data set DF2, creates a subset of that where the date is equal to the deadline. and I keep the maximum temperature. So when you run that one, it's just going to give you the maximum temperature that is at the very end of my data points, which was 57. This was the very last maximum temperature. So, how do you do predictions then? Well, you take that last value, and you add the seasonality, and measure, you add 2 standard deviations together. You can omit that part, the 2 standard deviations, and there's not going to be a big difference. But this is a heuristic that I found works in practice. Let's omit now that and just do the last value of 2014 plus the seasonal vector. And put a little comment here and run this line. And this will give you a vector of predictions for 2015. But this is a vector, right? So we need to change it back into a time series. And that's what the next line does. Again, I need to tell it where to start this time series and to do it daily. Right? So the next line takes this prediction and turns it into a time series. And finally, we plot it. So there you go. That's the prediction. It's actually calculated for the whole period. Everything from 2014 all the way to the beginning, I think.
So it comes from the right of like random.
Yep. So the standard deviation of the random noise. So the reason why I added these standard deviation is these type of analysis always underestimate. So you should always add a little bit of standard deviation. There are many ways to add that standard deviation. You can add it at random, or you can just straight up add it in there. So this is a good calculation. This one with standard deviation is a good calculation. This one minus standard deviation is a good calculation. So obviously you're not going to get a best prediction, but you're going to be off by at most 2 standard deviations. That's why I'll come back here and add the 2 standard deviations and redo this. And now, nothing much changed, it's just that my graph got up a little bit. So you need to create the one with the plus 2 standard deviations, you need to create the one with minus 2 standard deviations, you need to create the one without any standard deviations. And somewhere in there is your best mix. And this prediction is much better than our email. Okay? Especially for weather data, especially for things like this. Alright. Now, we have a couple more things that I want to discuss, but I'd like to pause here and give the floor to Nga so she can talk to us about her project. We will continue with these ideas, and the one thing that I want to talk to you about tomorrow is how do you continue on with this prediction, and how do you find peaks and problematic areas. Any questions before we close this? I hope you guys put results, put comments, because your task is going to be do the same things with the minimum temperature, basically. Okay. Which is the column right next to it. But you'll have to explain to me how that's your homework. Column 3. All right, let me stop this real quick. And you want to bring it forward, we can connect things, and hopefully it's going to work.